Good morning, everyone. Thanks for joining us today. This is the third installment of CED's webinar series. Today, we'll be speaking about biomechanics of fitness and recreational sports. I am Tim Caton. I'm out of Shelton, Connecticut. I handle new case management. And with me today, I have Dr. Gary Brock from our Annapolis, Maryland office.
Hi, everyone. Thanks for joining.
So a little background into Dr. Gary Brock. He has a PhD in mechanical engineering, a focus in biomechanics. Typically, he opines on cases involving workplace safety, product liability, motor vehicle collisions, and premises liability. Gary, some people might not know what biomechanics is and what a biomechanist can offer at a trial or deposition. Can you give a brief background into that field?
Sure. So biomechanics is basically the application of mechanical engineering to the human body. A biomechanist looks at the human body the same way that a mechanical engineer would look at a piece of machinery or a car. The difference is where the mechanical engineer would be looking at the strength of the frame of the car, we're looking at bones. Where the mechanical engineer would be looking at the motors for motion and things like that, we have muscles. Where the mechanical engineer might be looking at a pump, we have a heart. So we're basically using the exact same principles that a mechanical engineer would use and just a slightly different application. So from biomechanics, what we're applying is both engineering and physics principles along with medical knowledge to try and understand how forces and motions interact with the human body.
So today we're talking about recreational sports and fitness. A lot of people now are working out at home, stuck inside, kind of doing at-home workouts. So when I start a typical workout session, I start with a stretch and do that to kind of warm up the muscles. What type of injuries could we see when stretching or possibly doing yoga?
So when you're doing these types of activities, you want to be sure that what you're doing, you have the proper form as you're doing these things. If you have improper form, you might be putting excess load on part of your body. You might be doing something that would be unexpected or unintended. You might be pushing your body to the end of its range of motion. So when you look at how the body moves, we always talk about a range of motion. That's basically the total amount that your body is capable of moving. You may accidentally be pushing your body towards the end of the range of motion or potentially outside of that. And these are things that can lead to large loads on joints, on different structures in the body. And when you're creating larger loads, you certainly have the potential to then create injury. As you're doing yoga, we're looking at YouTube right now and having a yoga mat in our living room instead of being in a classroom. We don't have someone there going, here's how you should be bending. That maybe your hands should be taking more of the weight as opposed to your legs or your spine or some other portion of your body. So understanding that proper form for doing these activities can be really important because you don't want to accidentally be creating a larger load than you intend to create.
So after my stretch, hopefully barring no injuries, I'd like to get a sweat on, do some cardio. I know a lot of people that like to run or ride a bike on the road. I prefer a spin bike. I have the instructor on my TV in front of me yelling at me, motivating me. What type of injuries have you seen with bicycles or maybe running on the road?
Mm-hmm. Well, looking at things like spin bikes and bicycles, there's a huge difference between a spin bike and a bicycle. When you're using your bicycle, you're pedaling, you're going down the hill, you're going really fast, and you can stop pedaling and the bike keeps going. A spin bike doesn't work that way. A spin bike has a direct drive between the pedals and the flywheel at the front of this. So the faster you pedal, the more energy that gets stored in this flywheel. So as you're pedaling and pedaling and pedaling, you're generating more energy that's being stored within the system. The difference is that energy is now stored and needs to go somewhere. And the pedals keep going as long as that flywheel is moving. There isn't what's called a free hub in there where the flywheel is able to spin without spinning the pedals. And what happens here is that to then stop the bike, you need to make sure you hit that big red button in the middle of the bike frame, or have some other way of slowing it down to make sure that you're not generating a very large load on your legs, your ankles, things like that. if you were to just suddenly stop, you could generate really large loads on your ankles, on your legs, or if your foot were to say come out of the pedals, you could have that pedal come around and strike your leg. So this is kind of a big difference here, is that you have this large disc that can weigh 30, 40 pounds spinning at, sometimes somewhat high RPMs, causing these pedals to spin around again. And you don't want to get your leg caught in there. You don't want to try and force your body to stop it. You want to make sure that you're using that button to stop it, that you're allowing the friction of the system to slow it down, and not trying to do that just through your own weight.
So we spoke about bikes a little bit there. What type of injuries could you see while running, maybe on a track or on the street?
Certainly, there's a big difference between running on a track and running on a street. If you're running on a track, you're running on a planar surface that oftentimes could have sort of a rubberized textured material that's really made for having good traction. It's flat, you don't have to worry about a whole lot. If you're running down the street, I know, at least my street, you have potholes, we have areas where someone was working on their car and there could be some oil in the street, you could have a pine cone, you could have all kinds of things. You have a very different surface, so you need to be very cognizant as you're going along of, hey, there could be a discontinuity in the running surface that could cause me to trip. There could be something where I could roll my ankle. I could slip on this spot. You want to make sure as you're going along that you have a planar surface, and it is quite different than a track where you kind of don't have to worry about that and can just try and make sure you make the next lap faster than the last.
Nice. So we have our sweat going, heart rate's up. So now we want to start lifting. What type of injuries have you seen with weightlifting?
So weightlifting, you're putting a whole lot of load on your body, and that's kind of the whole point of it. You're trying to push your body towards the amount you can lift to try and grow more muscle. As you lift more, you can kind of be like Rocky, you're getting stronger. Your bone and your muscles react to this loading and grow. The issue is that if you're not doing this correctly, you can then induce loads in ways that are unintended. So as you lift up that barbell set, you're putting a large load, compressive load on your entire body. You want to make sure that you're just putting that compressive load. If you have it in front of you, now you have a bending moment where you're actually getting pulled forward. So we need to look at how the body reacts to all these loads and make sure that we're not accidentally doing something that's unintended. Specifically with weightlifting, we want to make sure we're using proper form and potentially like the machines that they would have at the gym. When you go to the gym, we have these squat racks and things like that where you can make sure you're going and lifting everything in a very specific manner. And also they have safety stops. If something goes wrong, you can let go of that weight and it'll get caught, and make sure that you're not going to accidentally get hit with that bar or something like that. So when you're doing these types of workouts, it's worth noting there's a big difference between doing them at home and doing them in the gym. The gym has the ability to prevent you from, accidentally moving outside of where you want to go, accidentally creating a load that you aren't intending to create. Or if something goes wrong, as a safety stop to make sure you're not going to get hit by that bar with 50 pounds of weight on it. You're not going to get your arm pulled back in a manner that isn't something that's going to be good. It's going to constrict the motion to what you are intending to load and hopefully prevent you from moving outside your range of motion.
So you brought up the point of using all-in-one gyms or gym machines as a way to prevent some injuries. Is there other safety equipment maybe for yoga or sports, and is it really needed?
Definitely. When you go to the gym, you'll go through there and you'll notice there's mats everywhere, there's padding. Most of the time the flooring has somewhat of a rubber surface on it. What we're trying to do when they do that from a biomechanics side is basically increase the stopping distance. What a safety mat really does is it just creates a softer surface. So when you strike that, you're going to move into the mat. You're going to increase the distance over which your energy is dissipated and thereby reduce the accelerations and forces experienced by your body. And that's kind of the whole goal, is just to make sure you can reduce those accelerations. So when you're in a gym, you have safety mats everywhere. If you were to fall or something was to go wrong, you're going to strike a softer surface. This is going to increase the distance which you stop, increase the time that it takes for you to stop, and lower the accelerations and hopefully lower the forces on the body. You can use braces and supports. You know, a brace around your knee, it's providing extra support for that knee to try and help you as you lift something, make sure it might be a little bit easier for you. It also restricts motion. You know, if you have braces where it's holding it from lateral motion, that can prevent something from coming in from the side and, say, injuring your ACL or causing some other kind of knee injury. The other thing we always have are helmets. Helmets provide increased protection. Certainly a helmet is going to prevent you, hopefully, from getting a bruise if you're hitting the head, but it also reduces these accelerations. So when you're wearing a helmet, the whole idea is that it's going to take longer for the force to get dissipated. It's going to increase the stopping distance and hopefully lower the accelerations experienced by your head, and potentially lower the total motion that your head will experience. All these things, lower accelerations, lead to lower forces and hopefully a lower chance of injury.
So you brought up the point that we want to decrease or increase distance and try to decrease the acceleration of something. With COVID going on, everyone's talking about flattening the curve. Is this the same idea of safety equipment?
Exactly. You really kind of do want to flatten the curve for accelerations. You have basically a fixed amount of energy you're trying to dissipate, and when you have a longer time, the accelerations tend to go down. A lower acceleration will lead to a lower force, and that's really the key thing. Force is mass times acceleration. So the lower the acceleration is, the lower the force should be on your body. So what we want to do is try and have something where you have a greater stopping distance, you have more time that you're in contact with. A helmet would be one example, a crash pad, a gymnastics mat. These things all increase the time that's going to take you to dissipate that energy to stop and hopefully lower the forces experienced by your body.
So you get a case where an injury occurred and they want to test against it. How do you do this?
So what we want to figure out is what are the accelerations and what are the forces experienced by the body. So one way, in this example, we would have a head form. We want to see what the accelerations to the head would be. So we would use a full human ATD. So these are crash test dummies, SAE specific ones. And we can take an object and drop it onto the test head and get the accelerations. So in the center of that test dummy, there's actually a 3-axis accelerometer as well as a 3-axis gyroscope. So we're able to now get the accelerations in 3 directions as well as the rotational accelerations. Then we can take those numbers and look at some biomechanics data to look at the propensity for injury based on what we've seen in biomechanics literature and begin to analyze, you know, where we're at and what the chance for injury would be.
Is there anything else you would look at, Gary?
So really each case is completely unique. We need to look at how the motions would be, how everything would be striking the body would be, how the different forces that could be involved. But looking at, you know, just what everything, all the things that occurred in the incident. So the other thing we can look at is the medical records. You know, in the case of a fracture, for instance, the pattern can indicate how a force was applied to the body. So we can then take an X-ray, a CT scan, an MRI, and begin to back out how the forces were applied to the body. And in this figure here, you can see there's different types of fracture patterns that are consistent with different loadings to the body. You can have direct fractures, which are consistent with sort of a high energy event. We call it comminuted fractures. So these would be like, you know, something extremely hard hit the body, or you have a crush type injury. The bone just breaks into a whole bunch of pieces. Then you can have things that are indirect fractures. So these can be loadings that didn't occur at that part of the body. You can get things like a bending fracture where someone ran into the side of your leg. You know, football tackle, you may get hit in the femur and it'll break in the middle because the femur is actually getting bent. You can have a torsion fracture. This would be consistent with someone skiing down a mountain and they're wearing a ski boot and it happens to get caught in the snow. They spin around and it creates a rotational injury. You can also see these sometimes in, you know, people tripping and falling, twisting their ankle. We have traction injuries where you can have perpendicular forces, so something where your knee got caught, say, or something like that. But in all these cases, we can take a look at the medical records. We can take a look at the x-rays, the radiology images, and try and back out what the forces would be needed to actually cause that injury, and then begin to understand how these forces would have been applied to create what is alleged.
So I think this next slide is a great example of an actual medical x-ray. What do you see in this, Gary?
So what you're looking at here, this is an x-ray of a right ankle. You can see the tibia and fibia, and you can actually see that the tibia has a fracture through the bottom part, and it's a spiral shape. So what this indicates is that there was some kind of torsion applied to the bone or some kind of rotation. So someone caught their foot and it got spun around, and that's what caused this fracture. This can occur, skiing type injury, lots of different ways in sports, something where basically your bottom of your leg just got spun, and that's what happened here. But it can be very useful because in cases where we're trying to understand how the injury occurred, we can take these kind of images and back out at least what the necessary forces would be.
Thank you, Gary. There's great information there. Thank you all for joining us on this webinar. If you have any questions, you can put them into the Q&A on the webinar right now, and we will answer any as much as possible. If you have something a little more personal about a case or an assignment, you can call us on these direct numbers, or you can always submit an inquiry at www.cedtechnologies.com. Gary, we just got a question. What's the difference between a biomechanist and a physician?
So the difference between a biomechanist and a physician, I don't see patients, I don't diagnose patients, I don't do any of that. I'm not going to be prescribing any kind of medication. I'm not qualified for that. I don't want to do that. The difference is the doctor, though, they're looking at trying to understand what the diagnosis is for the patient and treat the patient. They're not looking at what the anatomical forces were to the body, typically. They're going to be trying to look at, here's what the injury is, here's how we treat it, but not trying to look at if there's consistency between the forces of the incident and what's being alleged, the damage to the tissue. That's really the difference there, is from the biomechanics side, what we're looking at are what are the forces and motions that were applied to the body, and are they consistent with the damage to the tissue and the injury that's alleged.
Thanks, Gary. We have another question for you. How do you relate these injuries to daily activities?
So really every case is different. What you're doing is you're looking at what the accelerations would be in daily activities and trying to understand how those accelerations could impact the human body. Certainly when you look in the literature, there's data that suggests what loadings are for activities of daily living. But we're also looking at sort of what the loads would be on the body. There's a lot of data out there suggesting things like for lifting. There's a NIOSH lifting criterion. There's Snell push-pull tables, and these are things where we can begin to take a look at what biomechanically has been shown to not cause injury and what the loads for that would be. There's lots of biomechanics data out there. There's different sources for data where we can begin to understand what the loadings to the body would be.
Gary, we have one more question. Does increasing elevation grade angle on treadmill affect the chance of injury?
That's a great question. It could be, it kind of depends. If you're increasing the elevation, you're going to be putting a higher strain on your body. You're pushing harder to go up that the treadmill. You are going to be putting a little bit higher load on the body. Whether it could create a higher propensity for injury, I mean, anytime you're going to be pushing your body harder, you're putting a higher force on it. So I don't know how much more it would increase, but certainly the more resistance you apply to your body, the larger the forces to your body would be.
One more, Gary. We hear a lot about low-speed impact injuries in cars. Have you investigated any of these?
Yes, we do quite a few of those, trying to understand, what the accelerations to the body would be. We've done everything from low speed to high speed collisions. Pretty much any spot where we're trying to understand what the loading to the body would be, and what the kind of motions to the body would be, or something that biomechanics and biomechanical engineers are taking a look at.
We'll give one more minute to see if anybody has any more questions. If not, we'll wrap up, but feel free to reach out to Gary or myself if you have any more questions. Gary, thank you for your time. I think that is all. And thank you all for joining us on this webinar.
Thank you, everyone.
We will continue the series, and we'll keep you posted on the next webinar. Thanks.